Machine learning process is an optimization process. We usually define a loss function and then find the parameter that minimize the loss function. That is the typical process of your machine learning. Even in deep learning cases, we have to find the parameters that minimize the loss function. Okay, so let's say this is theta star. Right. So how can you find the theta star? If the loss function is very simple form like convex shape or some very simple function, then it is very easy to find the theta star. There is many tons of algorithms that can find the optimal solution. Convex optimization theories and many optimization theories can give you very nice approach that can find the theta star. But unfortunately, most of your machine learning algorithms will have totally non-convex, very complicated function as the loss function. So indeed, there is no universal machine learning algorithm that can easily find your theta star immediately. Okay. But gradient descent algorithm is very nice approach that can at least provide you local optima. So here local optima means so this is gradient descent. So what is the local optima? So let's say the theta dimension of theta is 1. So only single input predictor or input variable there. And this is the loss function shape. Okay, so this is non-convex function. Okay, by the way, the convex, non-convex, the definition you can easily find from Google. So I'll not cover such simple thing here. Okay, I'll skip that. All right, so this is a non-convex function, and there are two local minima. So local minima means locally. So when you look at some very tiny neighborhood, if the point is the lowest value or the least value among very tiny neighborhood, then we say the point is local optima. Okay, so the local optima usually very nice. So although all the local optima is not global optima that really minimize the loss function, but some cases or many cases, usually in machine learning, deep learning cases, local optima is enough. We are very happy with local optima. All right, so gradient descent algorithm is a very nice approach that can find the local optima from very complicated non-convex loss function. Okay, so in this video, I will briefly explain what is the gradient descent approach and why gradient descent approach can give you the local optima point. So the gradient descent approach is very simple. So it iteratively updates your parameter value. So let's say theta t plus 1 denotes the parameter value at t plus 1's iteration. This is theta t, the parameter value at time t, minus some constant times gradient of your loss function at theta t. This is gradient descent algorithm. Very simple. And this constant is called the running rate or step size. And this can also function of time, so you can change the step size over your iterations. Okay, so this is called learning rate scheduler, and recently many learning rate schedulers are invented for deep neural networks, and such learning rate scheduler improve the test accuracy in many scenarios. Okay, so this is gradient descent algorithm. So to understand the gradient descent algorithm, we have to understand what is the gradient. So gradient is this. When there are d number of parameters, the gradient's definition is the vector consists of partial derivative with respect to each parameter. And the partial derivative essentially for I is this. Here EI is all zero vector except one element where the location is i's coordinate. Okay, so this index indicate the index of vector that having one value. Okay, so this is the definition of a partial derivative, and this is the definition of gradient vector. So essentially, the gradient vector consists of full of partial derivative, and partial derivative means when you control the i's element very tiny amount, infinitesimal amount, then how much variation you can observe for the loss value. So this very tiny amount is very important. All right. So when you learn gradient descent algorithm, and essentially the gradient means, so to understand the gradient descent algorithm, I will bring the simple example from 1D input case. Okay, the gradient indicate the slope. Gradient at this point indicate the slope of the tangential line. So when you move to the opposite direction of your gradient vector, you can expect decrease of your loss value. Okay, so imagine the loss function is really linear function. Okay, imagine the loss function is really linear function. Okay, then what will happen with gradient descent algorithm? Zeta t plus 1 is equal to zeta t minus gamma gradient L zeta t, right? Since the loss function is the tangent line at this point, this is loss value at zeta t plus gradient of inner product between gradient of L at zeta t and zeta. So when you put zeta t plus 1 here, you have L zeta t minus gamma times gradient of L at zeta t normed square. So since this value is non-negative, we can say that L theta t plus 1 less than or equal to L theta t. This is great. We can guarantee the gradient descent algorithm always decrease your loss value. And the equality holds if and only if gradient as theta t is equal to 0, which means theta t is at the local minima or local maxima or some critical point. Yeah. And essentially this is very nice point indeed. So this is very nice property of gradient descent algorithm. But in reality, we don't have linear function. We have very wiggly curved loss function. So this assumption totally does not hold. Right? This is approximately hold for the theta in the very tiny area, t from theta t minus epsilon to theta t plus epsilon with epsilon very small. This is a hold. But when the range becomes bigger, this equality does not hold, so we cannot guarantee always decreasing property anymore. Right. So in practice, we have to very carefully control the step size or learning rate.